With our next lesson in this unit on powers and roots. And this topic is scientific notation. I'm going to start on page 153. And there's a picture of a globe here because it's talking about the distance between the Earth and the Sun being 95 million miles, a very large number. Speaking of very large numbers, what is the mass of the Earth? Mass, of course, being the amount of matter, kind of like the weight, except without force, right? So the mass of the Earth looks like this. That's a big number. Okay, a big number. How do you say this measurement? How do you say this measurement? Well, you kind of count back here, so I'll leave that one to you. It reads like this. Okay. Here's another question. How big is the COVID-19 virion? Okay, the particle, the virus particle, virion maybe it's called. Okay, here's a red blood cell. The coronavirus is this guy right here. A coronavirus virion is 0.000001 meters in diameter. How would you say this? 1/10,000,000th of a meter. Okay. So in science, quite often you have very large numbers like the mass of the Earth, very small numbers like the microscopic sizes of things. And there's really a better way to write these things than having to write out all these zeros, either after a decimal point like this or after the big number like this. Okay. And that method for writing these types of numbers is called scientific notation because it's used in science a lot. Okay, so scientific notation is the way to write a number by having a number between 1 and 10. So just a single digit number. Okay, well, single digit to the left of the decimal point. Okay, then a multiplication sign and then a power of 10, 10 to the sixth in this case, or 10 to the negative fifth. Positive powers of 10 for very large numbers. Negative powers of 10, right? This is actually 1/10 to the fifth, right? So this is a small decimal number. Negative powers of 10 for small decimal numbers, okay? And the exponent tells you how many powers of 10 there are in the number, okay? So what you should be able to do is to convert back and forth from scientific notation to standard notation. Standard notation is the way that you normally write numbers without exponents, okay? So if you're given a number in standard notation, can you write it in scientific notation and vice versa? So here's how this works. An example, to express a number in standard form when it is given in scientific notation, 2 times 10 to the third. Well, this 10 to the third is actually 1, 2, 3 zeros, right? Multiply times 10 times 10 times 10. So you take the decimal point where it is in your scientific notation number and you move it this many places to make this number bigger because it's a positive power of 10. So 2 times 10 to the third is 2,000. 6.8 times 10 to the fifth, 1. The first place is the 8. And then 4 more. So you add 4 zeros on the end of this. A common mistake is that people will just add 5 zeros to this number. But if there are digits after the decimal point, they take up some of these powers of 10, some of these multiplications of 10. So it's not writing 5 zeros afterwards. It's moving the decimal point 5 places to make a bigger number. For small numbers, the decimal point has to move to the left this many powers of 10. So 3.25, we start with the decimal there and we go back 1, 2, 3, 4 places. So you end up with 3 zeros, 0.000325. Okay, there's a few for you to try on your own. We'll practice a bunch of these, but here's 3 in the presentation. 4 times 10 to the second in standard notation. That's 400. 5.94 times 10 to the seventh. That's 59,400,000. There are 5 zeros after the 4 because the first 2 powers of 10 are taken up by the 9 and the 4. 1.3 times 10 to the negative third. Negative power of 10 means a small number, so this is 0.0013. Okay, to go the opposite direction, if you're given the number in standard notation, changing it to scientific notation, you take the decimal point, wherever you start in your standard notation, and you move it until you get a number that is between 1 and 10. So you move it until there is one digit to the left of the decimal point. So the decimal point starts at the end of this number because there isn't one. And you move it 1, 2, 3, 4, 5, 6 places to get 4.0 or just 4. So it's 4 times 10 to the 6th. Large number, positive exponent. 0.072. I'm going to move the decimal point 1, 2 places till I get a number between 1 and 10, 7.2. And so it's 7.2 times 10 to the negative 2 because I moved it 2 places, and this is a small decimal number. So the power of 10 is negative. 900 in scientific notation, 9 times 10 to the second. 18,900, 1.89 times 10 to the fourth. Carry all the digits that are not zeros in your answer here, unless you're going to estimate, which we'll do in a second. And the last one, 1, 2, 3, 4. 6.4, that's my number between 1 and 10, times 10 to the negative fifth, because this is a small decimal number. Estimating is very common with scientific notation. You might have a big, like the population of Kansas, for example, is 2,853,118 people, for a minute, and then somebody's born, and then it becomes 119 people, and then somebody dies, and it goes back, right? It's kind of ridiculous to have this number go all the way down to the single digits. In fact, it's really ridiculous to have it even go down to the thousands. So a lot of times large numbers like this will be estimated by a scientific notation. So 2,800,000 blah, blah, blah is about 3 million, okay? Or we're just going to round this to one digit and call this about 3 times 10 to the sixth. 3 times 10 to the sixth people is about the population of Kansas, okay? Now, the book now gives you a couple of examples here. And I don't like making one-digit estimations for numbers that end in a 4, 5, or 6, okay, that are closer to a half than they are to one, either the number before or after, okay? So 3,600,000, I would not round this to 4 million, okay? I don't round it to 3 million, obviously, okay? I would round this to 3.5 million, 3.5, okay? So a lot of times it's kind of like rounding to the nearest half instead of to the nearest whole number. That's really better math to do that. So I wouldn't give you examples like this. If I was telling you to estimate, I would give you something that's closer to 3.7 or 3.8 or 3.9, okay, or maybe 3.1 or 3.2. But if it's close to 3.5, then that's how I would estimate this. I would estimate this as 3.5. 1, 2, 3, 4, 5, 6. 3.5 times 10 to the sixth. The book would probably say this answer is 4 times 10 to the sixth. Okay, but that's off by 500,000. That's pretty big number. This one, again, 251 at the end. So my decimal goes all the way here to 2.51. I'm not going to round that up to 3. I'm going to round that to 2.5. That's a good estimate. And it's a nice round number. There's nothing wrong with this math when you're doing an estimate to round to the nearest half. The last one is already in scientific notation, but you can round this instead of 4.215, just round this to 4, about 4 times 10 to the negative third kilograms. Okay, so this is, just a basic math discussion of reporting numbers in a simpler form. This last part here is it's a requirement in the Common Core, which is why they have these questions. I'm used to teaching this in 8th grade. This is an 8th grade topic that sort of comes out of nowhere, all right? But it's basically talking about what the best way is to report numbers, okay? And the basic situation is that if the numbers are large numbers, then you should report them with the largest units that you can, okay? So this example, the space shuttle travels 8 kilometers per second. That's pretty fast. And it would take it 4.5 times 10 to the 4th seconds to fly to the moon. Or could you convert this 4.5 times 10 to the 4th seconds? That's the same as 12.5 hours. Well, which way is better to report how long it takes the space shuttle to fly to the moon? Well, 12.5 hours is better. Okay. And this is not right because it takes more than 12.5 hours, I think. But anyway, the answer to the question, is it more appropriate to report it as 4.5 times 10 to the 4 seconds or 12.5 hours? The answer is 12.5 hours. And it's not because it's not in scientific notation. It's because 12.5, because hours is a larger unit than seconds. And this is a big number. So if you have a large number, then use the larger unit of measure. Okay, and their example on this one is a dime, about 5.875 times 10 to the negative third feet. Okay, 5.875 times 10 to the negative 3 feet in diameter. Okay, well, is it better to report it as that number, 5.875 times 10 to the negative 3 feet, or 7.05 times 10 to the negative 1 inches? Okay, now these are both scientific notation, so it's not because one is and one isn't, because it's easier, right? They're both in scientific notation. What is the better unit to report the diameter of a dime? And the answer is 7.05 times 10 to the negative 1 inches. Why? Because this is a small measurement, so you should use the smaller unit, which is inches. Inches are smaller than feet. That's it for this one. We will continue on more scientific notation topics in the next lesson.